Okay, everybody, thanks for joining. We can't really hear you, but I hope you can hear us. So we're going to cover a bit about the Tuki network and the Tuki protocol. Basically, let's start with the way things are today in the Web3, right? So this is going to get slightly technical very fast, so try to keep up as we basically lay out the fundamentals here. So right now in Web3, there is a dichotomy between speculation and dev tools. That means that either there's a lot of dream factories and exchanges, or basically a lot of a tortoise tower of developers building dev tools for developers, building dev tools for developers. And then another dichotomy we've seen is that basically you have either products that are built then waiting for the infrastructure, or infrastructure then waiting for products that can use them. And this is why Tuki Network is a product first, protocol first, which means that we don't just developing protocols waiting for someone to use them, and we're not just developing products waiting for infrastructure, but we're developing the infrastructure we need in order to actually bring value. And right, we all want to bring value to users, and that's what's going to bring the entire ecosystem up, right? But in order to bring value, you need to actually provide novel utility for end users. Now, we're not going to go into why we believe this. This is another discussion, but our view is that battle-tested decentralization is the only feature, the main feature of Web3 and this revolution. Everything else is just supporting means towards an end. Now, that being said, looking at truly distributed virtual machines, we need a layer 2, because if it's going to be really secure, it's not going to scale, and then you need layer 2. Now, again, not going into why we believe that, it's another discussion, but state channels rule layer 2. There were some convincing talks before, I'm not going to go into why, but basically if you're relying on side chains or plasmas, etc., you're basically then undermining the basic principle of decentralization. And when you're using state channels, basically things are resolved as they happen. It's a more decentralized approach. Lastly, current state channel solutions often require a lot of setup. So you need users to first be on Web3, have addresses, have ETH, then set up some multisig, then they can go on layer 2. But there is no people on Web3, so no one has Ether. So let's go into Web 2 present. Now, no one has ERC20 clients. We first thought, oh, ERC20 clients are the new browsers, but no one has them. But everyone has HTTP clients, right? HTTP is the only etheric, decentralized part of Web 2.0, right? And no one has Web3 wallets. No one currently, and when I'm saying no one, I mean not everyone in this room, but like the 99.9% people outside of this room. No one knows or wants non-custodial ships. Usually, most people aren't ready for non-custodial ships. No one has an active address in Web3. No one has Ether, or most of them don't even want Ether. And no one actually knows how to easily or seamlessly get Ether. So, we still want to bring everybody there, right? We want accessibility and scalability for Web3. So, largely speaking, what's our spec? Well, anyone should be able to create smart contracts and participate using nothing more than an HTTP client. And in the current version, also internet connection is required, but next versions, you can transmit it just directly between devices, etc. Second, actually integrating into smart contracts and interplaying with them shouldn't require any prerequisites, because no one is there. If you're going to say to people, look, we have this great solution, but please first understand what Ethereum is, get a wallet, get a non-custodial thing, get some Ether, build a multisig, then you can go up to layer 2. That won't work because everyone's there, they're not here. And of course, the last thing is most transactions should not depend on layer 1 in real time. That being said, largely speaking, Ethereum is a backend. So users should not directly need to know anything about it from a utility perspective. Our approach to bridging this gap is HTTP-based multi-party state networks. So of course, the idea is to offload transactions from layer 1 to layer 2, where the layer 2 is an off-chain network of web browsers acting as decentralized nodes in multi-party state networks. Now, the link sharing basically is a means of adding new people that are unknown right? Because if you need to know the parties in advance, if they need to have Web3 wallets in advance, if they need to, in advance, create a multisig, you don't know who's going to join, right? If it's web scale, you just need to let anybody join with no prerequisites. By browsers for browsers, it means that the browsers themselves are the means to distribute state, to hold state, to manage state for majority of the transactions of the smart contract. Basically speaking, that means that in the full spec of this, when you create a smart contract, the smart contract is persisted to layer one. But in that act, a multi-party state network is raised, which can then be played out by an unknown group of users just using HTTP clients. So all of those transactions afterwards are happening off-chain, yet in a decentralized manner, and then persistence to layer one becomes an off-time, offline issue. It is eventually persistent, but the state is managed in real time, off-chain, on the network of browsers, and the browsers themselves are both the participants and the peers. In any distributed network in nature, you never find master nodes, you never find Ethereum nodes. The peers themselves are the means to create a decentralized network. Now, there is a roadmap. So what we're going to discuss today is the first part of it, which is called multi-party state chains, which means how we transduce a linear chains of transactions. Okay, that is good for a certain amount of contracts, and the product part of our project basically tries to implement one version of the protocol, one iteration, then say what product, what end user utility can we bring? And then we iterate the next part of the protocol, and we build some more product that proves that this can bring utility, okay? Because we don't want to go Cardano style and like tell everyone, let's meet in 10 years when everything's working, right? Because we want to bring utility to end users now, because that's the only way to get value into this network. There are two later, so this first stage is fully implemented. It's live on Ropsten. You're going to hear about the cryptography of this soon. It relates to how we relay linear state transactions on chains. That means any multiple parties in a linear state transaction. Think about like games, I go and then after you go. There's certain types of contracts that can be allowed by this. When we need to start syncing state between chains, we need two more steps. The second one we're working on right now should be finished this quarter, Q4. Which is pseudo managed, which means Plasma will do mining, but browsers will be able to validate and kind of go to layer one and report, and then there's some incentive models there. And of course, the fully distributed, this is really exciting, like the fully distributed part, which hopefully if we do everything right, should be available in like a year or a year and a half from now. It's basically using something we call fractal consensus. We're not gonna go into it now, but basically it means that there are browsers acting as miners in a very local manner in a hierarchic temporal tree of the state machine of the contract. We won't go deeper into this now, but you're welcome to reach out to us if you're interested in that part. Now, how do two-key links work? So basically, we came up with something we called it SmartLink. Basically, it looks like an HTTP link, but it contains two hashes. First part is a code hash. That hash is basically tells the browser where in IPFS to load the JavaScript and TypeScript from, right? Because when you're running an Ethereum node, you're running a server. A Bitcoin node, you're running a server. You need to go to a centralized source of authority like GitHub and download a certain commit hash, right? Because if you change 1 byte, it's no longer Bitcoin, it's Bitcoin Cash, right? So browsers, you can't do that. You need to really maintain and ascertain that all the browsers are running the exact same version of the code. This is why there's a hash to IPFS to download the exact same version of JavaScript, then and TypeScript. The state hash is the more important part. With the code that the browser downloads, it is able to validate a state hash as a certain point in the state machine of the contract, and then generate a new hash when this user wants to interplay with the contract or further the state. Together with this ability and human link sharing, the state machine of the contract evolves. We're gonna go now into how this works for multi-party state chains. For this, I'd like to introduce our chief scientist, and I wanna give just a quick intro so why you should listen to this guy. So first of all, I think he's one of the most brilliant guys in the world, and I'm really unbiased. We've been doing some crazy tech stuff for a few years now. So this guy was like commander for like a decade in Talpiot, which is the most elite R&D division in the Israeli Defense Forces. Then he co-founded Algotech as CTO and sold it. It was a really good exit. He was one of the first engineers in Checkpoint, basically established Checkpoint America and behind a lot of their IP. And he's also co-founder, CTO of Mintigo, which is a successful company still running. It's an honor to have him with us. Udi, please.
Thank you. So I want to cover like very, let's call it down-to-earth description of what Eitan was describing. And just imagine you have an ICO and someone wants to sell coins in the ICO, and eventually people will buy the coins on the ICO. So usually you have like on the top layer, you can see you have a secret information like wallets, shared secret, private secrets like the lowercase y you see here, which is colored red. And eventually when there are transactions, you generate a public information, which is colored green here on the bottom, like the address of this user. And in between, we added an intermediate level, which are secrets that are shared between people that just propagate an HTTP link, which promotes the ICO sale. So there is a campaign contractor, the person who's running the ICO, and that person creates a HTTP link with a secret on it, which is colored orange here, and you see like the X here. And that link, let's say, is placed in a Telegram group, so people can locate this link. And these are the first group of people that identify this link share the same secret. So it's different from having a secret which is inside the wallet. This is a secret which is shared between a group of, let's say, 1,000 people that are the first layer, first seed of influencers. And you can generate a public information from that secret also in the same way that you generate public information from wallets that are completely secret. And that's the formula I wrote there on the bottom. So basically the process you have is that there is a HTTP link which is published to a small group of influencers. Influencer number 1 is one of them. And each of these influencers modify that link and generates a new link which has a new secret X2. And that is passed on to a different group of people that are now once removed from the original HTTP link. And the idea here is that eventually when there will be a conversion, when somebody will eventually buy the coins, that person will have to use the entire information in the link and send it to the contract in order to buy the coins. And that information in the link will generate a bounty for each of the people that were involved in the marketing process of distributing the link up to the converter. And the way to do that is simply that each influencer adds a signature in the link that he saw the previous secret. So to be more specific, let's say the contractor created the secret X1, and there are 2 influencers in the Telegram group that saw the first link. And each one of these influencers generate a different secret, X2A and X2B. And now the link will look something like that. There will be, as you can see, the address of the first influencer, a signature made with the secret X1 of the address, and then there will be a new secret, X2. And over here you can see actually there is a second influencer also added his information. The second influencer added his address and a signature that he saw X2 and eventually added X3. And what will happen eventually, let's say influencer number 2 wants to convert. He will send the entire link without the secret to the contract. And the contract, the solidity code in the contract will validate each of these blocks going backwards one by one. So you first do a recovery on the last signature and see that you get the same P2 that you were having in the first block, and then you perform a recovery of the address in the first block and see that you got exactly the address of the first secret, which was written in the contract when the first link was created. So the contractor has a task of writing like an anchor to the entire link system in the contract. And then all the links can be validated going backwards by running a list of signature proofs. there's a different way we can handle that, and that is that the secrets are just hash function of each other. So that saves the need to store in the link the public part of each secret. So the link now is much shorter. So before, each influencer taken 105 bytes, and here we can manage just by having 85 bytes, because here we don't need to save the public part of each secret inside the link. But in order to validate the link, the contractor had to store all the public parts of all the secrets inside the link. So the Solidity code in the contract only needs to do is to validate each of these blocks, compare the recovered address to whatever the contractor stored, and then the entire link is validated. And you know that you have like a chain of influencers, A1, A2, that brought you to a conversion. And you can then attribute a bounty to each one of these influencers. And so we covered like so there is we added also like a flexibility that each influencer can add a small parameter, which is how much percentage he wants from the total bounty that is available. And you can simply add that to the signature. And the link is up to now was 105 or 85, which is actually quite long, because if you have like 10 influencers, then you have like almost like a kilobyte of a link or something like that, which is like a very long link. And also, the identity of each of the influencers is identified in the link. You see the addresses. And also, you can take the link and swap one influencer for another. So there's so somebody can place you as an influencer inside the link that in a campaign that you weren't involved and you don't want to be involved. So these are like problems. So for that, we generated a more shorter version, which also solves all the security version, which uses Schnorr signatures. And so the campaign contract starts again with a secret, X1, which is generated by the campaign contractor. And as before, we will use the hash function, and all the public parts of all the secrets are stored in the campaign by the campaign contractor. And let's say the first influencer wants to convert, he simply proves that he saw X1 with using a Schnorr signature, is what you see here. And so all you need to do is to hide the value X1 by a mask value, K star, and send to the contract S star, which is now a sum of K star plus X, and the public of the mask value, which is R star. In this form, it's impossible to recreate the X value. So anyone who's listening to the transactions cannot go back and decide what the secret in the link was. And but however, what the contract can do, the contract can multiply S star by the G, the elliptical curve generator. And if you follow the equations, you can see that actually all that the contract codes need to do is to validate that S star times G is equals to R star, the public part of the masking value, plus this hash of the address times P, which is stored inside the contract. And in general, this is how it looks like. So on the top, you see what you saw like 2 slides ago, that every new secret in an HTTP link is a hash of the previous secret. And in addition, there is a sum of signatures, which is the aggregated Schnorr signature that proves that all the influencers along the way saw, each one saw their respective secret inside the link. And the R's are the public parts of this Ks, which mask the secrets. And somehow the R's prove who the influencer was. So, so this is how the links look like. And the conversion is done exactly as we saw before. Like the converter, the last person who sees this link simply adds a K star. This is exactly what we've seen before. But now there's also a sum of these Schnorr signatures, which is the aggregated Schnorr signature. And this converter needs also to send his R star. This is exactly as before. And a list of R values, which are the masking of all the influencers along the way. So the benefit now is that each influencer adds 32 bytes to the link. So this is much better than the 85 and 105 bytes that we had before. And also, the identity of each influencer is actually not known right now. It's completely hidden because all you have here is like this R value. And this is what the contract performs in order to validate. It's exactly the same formula as before, but just longer because you need to validate each of the small signatures, SI, in the sum of aggregated signatures. Now, the only question that remains is how exactly each of the influencers proves that he owns the R value here. And actually, here we had like to invent a little bit new cryptography. I mean, it's like very small addition. And the idea here is that the secret, the K, is actually in itself another Schnorr signature, which is made from two random numbers. And if you can see, they're both red, which means that remains completely secret at all times. And what happened is that the influencer needs only to prove at a later stage, after the conversion, that he owns R. And in order to prove that, all he needs to do is to send R bar and P bar. R bar and P bar are the public values of these two secrets, of K bar and X bars. And all that the influencer needs to do is to send these two values, and of course his address also, A1. And all the contract is doing is simply calculating this equation. He's validating that R bar plus this hash function, which includes the address of the influencer, times P bar equals R, which was stored inside the contract when the conversion has happened. And so that actually you can prove that there is no easy way of getting these two R bar and P bar value which will match your address. So you cannot come as a different user and claim, actually, I own this bounty. Okay, so this is like all the math here. Now, Eitan, you want to finish up?
So thanks for keeping up, whoever kept up. Just running very shortly before, whenever we say contractor, that means that the person who actually initiated the contract on layer one and then brought this two-key link, which enabled it to elevate to layer two. And that layer two, using this, means that anyone can join without an ETH wallet, without ETH, without having anything but just an HTTP client, and then that can transduce state. When we say influencer, that means anybody that contributes to the state. That can be any conversion for now. In this version, that isn't monetary. It can be a vote, it can be a move in a game, it can be whatever you want to add. That's what's called a fee or a parameter. It can be anything. It's just a piece of information that gets signed on to a sort of recursive kind of transaction of the state. So what have we proved that is possible with this? Well, basically you can recreate the entire business model of Facebook with this, because Facebook makes all of its money from target audience discovery. I know this because both of us worked for doing deep learning to optimize that for like the biggest publishers and brands in the world. Basically, if you're a business, if you have any kind of business result, you need to find humans that are willing and able to produce whatever you want, like to read your content, install your app, buy your services, read your content, whatever, right? So it's all about discovering humans. And then we're using this to allow anybody to basically mobilize the human network. We call it social sourcing, which is like incentivized activation of result-driven virality. So that means that in each of these campaigns, basically you decide what you want to do and you basically mobilize ad hoc decentralized networks to go and find your target audience. Oh, sorry, that's the wrong way. Basically, you can see it working live. We're live on Ropsten. You can scan this QR code. You're going to be landed inside a Tuki campaign, which is just a sign-up campaign for us. So you can like earn Tuki tokens. You can then earn more Tuki tokens for bringing in more people. It actually holds a quite interesting incentive model. You can choose whatever you want to keep and what we want to forward from whatever incentive is left. And when you try and just forward and share and earn following this link, you'll see that you in no step are required to generate a Web3 wallet or have ETH or anything. Of course, there's a ton more to it, but we're out of time. So thanks everybody for listening. If you want to know more, catch Tuki.network. Thanks for being with us.